Hi everyone, this is Bilal. Welcome to tutorial 8 entitled Physical Plan, intended for both MET and Business Informatics, okay, which is part of Database 2 course. So first let me grab my set of tools. We need a calculator and we need a scratch pad, my paint, and we need the lecture 8 slides. Yes, lecture 8. So during the previous tutorial we have talked about the query processor, the first component inside the database management system architecture, or the database engine. And yeah, okay. So during the previous tutorial we've talked about the query processor or the query optimizer. The query processor do the following 4 tasks. The first one is to parse the given SQL query, this query given to the database engine, and convert it to parse tree. The second step, or the second task, is to compute the best logical plan to execute the given input query. And part 3, or task number 3, sorry again, is to map or to build the best physical plan. And last time we've said that the physical plan is a set of actions to be taken, okay, in the hard disk and inside the random access memory to execute the SQL query. Okay, so the physical plan is a set of actions and it's composed of the data itself plus the operators. Okay, so today we will learn about how to build the best physical plan and what are the main components of any physical plan in details. Okay, so as we said during the previous tutorial, let's recap what we have been taught during the previous tutorial number 7. We learned about how to calculate the cost for a given logical plan, okay, using heuristics and cost-based optimizers. Okay. So as I have just said a few moments ago, today we will focus on the physical plan. This is query optimization part 2, physical plan, tutorial 8. Okay, so now we are going to learn about how the query optimizer builds the best physical plan. Okay, so the output of the previous task or the previous step is a linear algebra tree or a relational algebra expression. Okay, so now the query optimizer wanna transform this linear algebra tree into set of actions, okay, to be executed. Okay, these 2 bullets give us examples on how the query processor can optimize or alternate our SQL query by using existing techniques or creating an index on the fly or sorting the data. So you may enter a simple select and the query optimizer decides to build an index or to sort the data, or it's better for him to use an existing index, okay, to execute this select statement in a very fast way. So the main components of the physical plan are the relation, the data itself, and the operators, which act on the relation to produce the final results. So you can think of the operators as ready-to-use functions, already coded, and they are part of the database engine. The database engine uses these operators to execute any given SQL query. So the set of operators provided by or offered by the database engine define the physical query execution plans. So let's revise two different iterators or operators. The first one is the table scan iterator, and the second one is the bag union. Okay, the table scan iterator wanna scan the table and load its pages from the hard disk in a very efficient and optimized way, okay, without the need to load the whole table inside the RAM. So instead it will read the tables, the pages, tuple by tuple, okay. So each iterator has three functions: open, close, and get next. In the open, we open the relations, and in the close function, we close the relation opened earlier, okay. So at first, in the open, we initialize. Think of this open as the init, the initialization method, okay. And this is pseudocode, okay. So this is the logic of the table scan iterator. So we will create two pointers. The first one points to the current block in relation R, and the second one is tuple T, which points to the current tuple in the current block, okay. So at first, B points to the first block and T points to the first tuple in the first block. Then function get next runs to iterate over the table tuple by tuple. So we have to check if the current tuple is beyond the last tuple in block. If we are finished with this block, okay, then we have to increment the block pointer to point to the next block, increment B. However, we need to check if the next block is beyond the last block. What if we stand here right now and we have reached the end of this block? We need to increment B, okay. So after incrementing B, we will point to another page or block that doesn't belong to the table, okay. So we have to check this condition. If B is beyond the last block, return more data. We are finished, okay. Else, set T to the first tuple of the new block, okay. So and retrieve the current tuple. Set old T, a new variable called old T, to the current tuple and increment the current tuple, okay, and return old T. And these three lines are gonna be executed in case T is not beyond the last tuple. In case T is at the start of the page, or in the middle, or at any position before the last tuple, okay. So this is the table scan iterator. The bag union iterator. The bag union, okay. Most of you who have already studied database 1 course, they should know or they should remember how the back union works. Okay, we open a third relation or a result set, and we get all of the tuples in R and put them or transfer them to the result set or to our bag. Then we iterate over the other relation and we insert all of its tuples inside the result set. This is how the bag union works. So at first I will have to open relation R, and I will set this variable current relation to R. So my current relation that the iterator or the operator is working on right now is R. Okay, so let's see. So right now I'm working on R, and I want to retrieve or return its tuples to be stored inside the bag or the result set tuple by tuple. So I will call the getNext function. Okay, so I will set t to r.getNext. Okay, fill t with the next tuple from relation R. If t not equal no more data, if I'm not finished with R, if R is not exhausted yet, return the current tuple. Else, if R is exhausted, well, we will have to open relation S, the second relation, so s.open, and we have to set current relation to S. So in the next iteration, okay, when the iterator call getNext, the iterator will check this condition, and this condition will evaluate to false because current relation equals to S. Then the iterator will exhaust S, okay, by calling s.getNext, 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 and so on. Okay, and in the close function we have to close the two relation R and S that we have opened earlier. Okay, so database engine has many iterators and many types of operators. We have just seen these two operators. Okay, we can classify the operators tuple at a time, which can produce an output by reading few tuples from the relation the operator is operating on at a time. Okay, and for relation, in order to produce the first line of output or the result set, it requires the passing on the full relation. Okay, and for relation binary, same as the for relation, but the operator works on two relations. Okay, and also we can classify operators by algorithm type. One pass operator, it will pass for just one time over all the whole data or all of the pages of a given table to produce the output. And we have multi-pass. Here the operator has to pass many times to produce the output, and we have a very famous example of multi-pass operators. If we need, we can use the multi-pass operator if we need to sort the data, or we want to eliminate duplicates from a given table. Okay. So an example of tuple at a time or non-blocking operators, simple select or projection. Okay, the operator can produce output after reading just the first few tuples from the given relation R. Select, okay, and projection. And here's a few examples about relation at a time. Group by. In order to group a set of tuples by a given attribute, we have to pass over the whole table to count or to form the groups to form the groups or to count the similar records in order to group it by the given attribute. So this is a relation at a time. And here are a few examples of the relation at a time binary: the union, intersection, set difference, cross product, and join. Okay, and we will assume the following assumption: one of the relation is smaller than the other and fits in memory. So here's how the database engine will execute the union of two relations: set union, relation R and S. Or let's assume that R is the bigger relation and S fits into the memory, S is the smaller one. Then we will output all of the tuples of S. Okay, and for each tuple in R, we have to search inside the SS index that exists in the memory. Okay, we have to search inside this index, and if it already exists in S, we need to output, and if not, so let's visualize this thing, this concept. Okay, decrease. Okay, we have two relation R and S. Okay, this is our hard disk, and it holds both R and S. And here inside the random access memory, the RAM, we have created in-memory index for relation S. So we have an index here, index of relation S. So we want to output the union of both relation R and S. So I will output all of the tuples inside the relation S, which contains S minus R, the set of tuples that exist in S and does not, sorry, that do exist in S and that don't exist in R, and S intersection R. So the remaining is to output R minus S. So we will iterate over the tuples of the larger relation R, tuple by tuple, and for each tuple in R we will search inside the index. If it exists in S, we will skip it. Okay, and if it does not exist inside this index, we will output this. Okay, because we want to output R minus S plus S itself. This gives us R union S. And the same applies for the set intersection. Again, S is a smaller relation, and we will create an in-memory index for relation S. For each tuple in R, we will search inside this in-memory index. If it exists, we will output, and if it doesn't exist, we will ignore it. Okay, to compute the set difference R minus S, we will do the same. However, for each tuple of R, we will search if it already exists in relation S through this index, okay, or not. If it exists, then we will ignore it, else we will output, okay, because we want to output the set of all tuples that do exist in R and don't exist in S. Okay, the opposite, set difference S minus R, and again S is a smaller relation, and we have an in-memory index for this relation S. So now for each, okay, let's consider S as the output set. Okay, so we want to remove all the tuples that belong to both relation S and R, okay, because we want to compute S minus R. So for each tuple in R, we will search inside this in-memory index, and if it exists in both R and S, we will delete it from S. The remaining tuple of S is a set of output, which is all tuples that belongs to S and do not belong to R. The cross product is very simple. We will load relation S in memory. We don't need an index here because we are not gonna search for any value. Okay, the cross product is very simple. Just combine each tuple in R with all of the tuples inside S. So for each tuple in R, combine it with all tuples of S that do exist in the memory. Okay. Okay, so let's think about how or what are we gonna do to execute this join. Okay, if we want to join both relation R and S, what are the steps, or what are our physical plan? So if we are going to join two tables, there must be a common column that to be used to join the corresponding tuples. Okay, so get me a new scratch pad. If we have relation R right here, this is R, and another relation S. There must be a common column, for example Y, to join the corresponding tuples. Okay, so here's what's gonna happen. We will load S in memory, okay, in the form of balanced tree or a hash table. Okay, we will create an index for S inside the RAM. Okay, index hash table for S. Okay, and for each tuple in R, we will search inside this hash table. Okay, hash table, and if a matching happens, then we will join and output this pair of tuples. Okay, and there are 5 types of join. Okay, we have five types of join operations. Okay, we have the first one is iteration join. Second one is zigzag join, and the third one is merge join. The fourth one is join with an index, and the last one is hash join. Okay, so during this tutorial number 8, we will learn about iteration join and zigzag join, and these 3 types of join, the last 3 types of join, we will discuss it during tutorial 9, the next tutorial. Okay, so one of the methods to execute join operation is to load S inside the memory and create a hash table or B plus tree. Okay, and as we have just explained this method, we search for each tuple of R inside this hash table, and when we find the matching, we join the corresponding pair of tuples accordingly. Okay, so let's learn about the zigzag join. The zigzag join is pretty simple and a very creative method to join two relations or two tables. Okay, it works by creating two B plus trees data structures for both relations based on the common column y in each relation, okay, separately. So this is a B plus 3 for relation R over column Y, and this is a B plus 3 for relation S over column Y. And we will search in both B plus 3 using zigzag movement, okay? Okay, so let's see an example. Let's see an example. Okay, I will take a screenshot of this part and let's load it here. Open, discard, pictures, screenshots. Yeah, okay. So here we have the two B plus 3s, and as we already know, the leaves of the B plus 3 are sorted increasing order and are connected, okay, together using the sequence pointers that propagates left to right, okay, through the leaves, okay. So at first we will stand here, okay, in both B plus 3s. This is I and this is J, okay. Remember that the two list of numbers or the two leaves, okay, of both B plus 3s are sorted and increasing. They are sorted in an ascending order or increasing order. So 2 and 1, okay, 1 is less than 2. So let's skip this one and go to the next integer, since this is this list of integers is sorted in increasing order. So it's we have a high chance, okay, to find another two, okay, after this one. So we can match them and join the corresponding tuples. So I will move to this 2 and 2, join them, move this operators, okay, the upper one. Now 3 and 2, okay, 2 is less than 3, so move the J, 3 and 3, let's join the corresponding tuples, move the upper pointer, 4 and 3, 3 is less than 4, move the lower pointer, 17 and 4, okay, 4 is less than 17, so we need to increment the upper pointer many times, okay, until we find 17 here, or we reach a larger number than, or a greater number than 17. So 10, 11, 25 is greater than 17. So now we have to increment the lower pointer, 18, 19, 21, 22, 23. We are finished with one of the B plus 3. So we are finished, okay? So this is how the zigzag join works. And if we can store the minimum and maximum of each bucket, okay, of the B plus 3, we can use this information to jump the buckets that will not match with each other. So for example, if I know that the minimum value here and maximum value here are 10 and 11, and the minimum value here 17 and 18. It's obvious that we will not find any matching, okay, between these two buckets, so we can jump them by searching for the maximum value starting from the root, using log n steps, okay, and looking or starting the zigzag again, starting from the bucket after the maximum number. And we can do the same here, search for 18 and start after the 18. This way we have just jumped this bucket and this bucket, okay. Okay, so in order to evaluate a physical plan, we need to estimate the number of input-out operations, okay? Because the most expensive step in any physical plan is to load something from the hard disk, because the hard disk's read and write speed is very much slower than the RAM and the cache memory and the processor, okay. So we evaluate or we assess our physical plan in terms of the number of IOs needed to execute this physical plan. Okay, here's the diagram that illustrates the basic architecture of any magnetic hard disk, okay. The hard disk is composed of a set of platters, and this needle can read the same sector across different platters using one input-output operation, one IO move, okay. So if the data is stored in a contiguous way, okay, suppose that we have a page composed of 3 tuples, 1, 2, 3, and this page is stored in a contiguous way, which means 1 exists here and 2 exists here and 3 exists here. All of them exists in the same sector, okay, across different platters, which means this arm can read the whole page, the 3 tuples, in a single IO. So IO, input-output operation, per block, one IO per block. And if this page is stored in a non-contiguous way, which means 1 exists here and 2 exists here and 3 exists here, so the 3 tuples that belongs to the same block or page are stored in different sectors. So this arm or the needle has to perform 3 separate input-output moves, rotations and seek, okay, to read the whole page. So IO per tuple, we call this contiguous and we call this non-contiguous, and this will affect or has will have a strong impact on the number of IOs needed to execute a given SQL query. So here are some of the parameters we need to be familiar with. B of R represents the number of blocks containing relation R, and F of R represents the maximum number of tuples per block or per page, and M the number of memory blocks available to be used to load something or to read something from the hard disk. Okay. So let's solve this example. Let's perform iteration join over these two relations R1 and R2, given that the number of tuples T of R1 in relation R1 is 10,000, and the number of tuples in relation R2 5,000, and the f of r equal 10, which means each block holds 10 tuples, and we have 101 memory blocks available to be used. Okay, so we can perform the iteration join, okay, in 3 different ways or 3 different scenarios. The first one is to read each tuple from R1 and join it tuple by tuple with all of the tuples of R2, and this is too expensive. We can use the available memory blocks to enhance the performance, as we will see, okay, in the upcoming slides. So let's visualize the first scenario, the most basic one, and draw it. Okay, get me a new sketchpad. Here's the hard disk. Okay, this is the hard disk, and here's relation R of 10,000 tuples, relation S of 5,000 tuples, and this is the RAM, random access memory. Okay, the first scenario is to read a relation R tuple by tuple. Let's read a single tuple from relation R, okay, R dot T1 for example, and the second step is to join this R dot T1, okay, with all tuples of S, tuple by tuple. Okay, so we will pass over all of these 5,000 tuples, S dot Tx, unknown tuple number. Okay, so single IO to read a single tuple from R plus 5,000 IOs to pass over all of tuples in relation S and join them with R dot T1. Okay, however, this is for just a single tuple that belongs to relation R. What about the other, the rest of them? Multiplied by, or ask yourself, you can ask yourself, how many tuples are in relation R? 10,000. This gets us nearly 50 million input-output operations. Okay, it's too expensive. This is a basic scenario to perform iteration join without using the memory blocks, okay, the available memory blocks. Okay, a second scenario is to load relation R1, okay, chunk by chunk into the available memory space, and we will see that this will save us a huge number of input-output operations. Okay, so here's the second scenario. We have available 101 memory blocks. Each block holds 10 tuples, so these 100 blocks can carry 1,000 tuples of R. Okay, so we are gonna join these 1,000 tuples of R with all tuples that belongs to relation S one by one. So to load these 1,000 costs us 1,000 IOs, and to pass over these 5,000 costs us 5,000 IOs. And we will repeat these for all the chunks of relation R. Okay, how many chunks are there? how many thousands, one thousands in R? 10,000s. Okay, so we have to multiply this by 10. So for each 1,000 tuples in relation R, we are gonna load it into the RAM memory, okay, into the available 100 blocks, and we are gonna pass over. We will keep these 1,000 tuples until we pass over all the 5,000s of relation S and join them with this chunk. Okay, so the cost is 6,000 times 10, 60,000 IOs. It went down from 50 million to 60,000. Okay, so using part of the RAM as a swapping area to read chunks from the hard disk is very helpful and very useful. Okay, so let's try to load relation S into the RAM instead of relation R, and let's see the effect of this. Okay, we will load relation S chunk by chunk, and chunk size is 1,000 tuples, and we will pass over all tuples that belongs to relation R, 10,000 IOs. And how many thousands are there in relation S? 5,000. Okay, so 5 times 11,000 gets us 55,000. So loading the smaller relation into the swap area has a positive effect over the number of IOs needed to execute this iteration join. So now we are finished with reviewing the concepts, most of the concepts covered by the lecture, and my advice to you is to go and watch the lecture, then try to solve the practice assignment problems by yourself. And now we have to practice these concepts by solving practice assignment 8. Okay, so let's start solving these questions of practice assignment 8. Let's start by the last question, question 4. Okay, this is question 4. Consider two relations R and S, and the number of tuples for relation R is 8,000, and the number of tuples in relation S 3,000. The number of blocks to store relation R 800 blocks, number of blocks to store relation S 300 blocks. The number of distinct values in relation R for attribute A is 100. The number of distinct values in relation S for attribute A is 3,000. And we have 101 memory pages available to be used. Compute the minimum number of IOs operations needed to join these two relations R and S using the following 3 different cases. Okay, first one, iteration join without using the memory and tables are not contiguous. Case 2, iteration join without using the memory and the tables are contiguous. Case 3, iteration join with using the memory if the tables are contiguous. Okay, so let's solve this. Okay, step by step. Fine. New, discard. Okay. So first case is to join them. Okay, using iteration join without using the memory. So, and they are not contiguous. This is hard disk, relation R and relation S. R has 8,000 tuple and S has 3,000 tuples. 8,000 tuples, 3,000 tuples, and we will not use the available memory blocks in the RAM, so we have to load single tuple that belongs to relation R and keep it in memory and pass by all of tuples that belongs to relation S. So s.tx, one IO to read a single tuple plus 3,000, okay, 3,000 IOs to pass over all tuples that belongs to S, multiplied by the total number of tuples. Okay, we will repeat this for each tuple in R, and we have 8,000 tuples in R. So the solution for the first case is 8,000 times 3,000 plus 1. Okay, okay, 3,001 times 8,000, 24 million IOs. Okay. Case 2. Iteration join without using the memory and tables are contiguous. Okay. Second case, okay. Let's undo these steps. The second case, we will load single tuple from relation S, okay, S.T1. Sorry, we will load 100 blocks of relation S, okay, and these 100 blocks can hold 1,000 tuples. So if they are contiguous, okay, so we speak in terms of blocks, not tuples, okay. So let's load S 100 by 100 blocks. So read 100 blocks from relation S costs us 100 IO because these two relations are stored in a contiguous way, plus passing over all the tuples, sorry, all the blocks of relation R, plus 800, okay. And how many hundreds are there in relation S? 3, okay, 3. Sorry, I have mixed between the second case and the third case, okay. Let's redo it again, okay. We will not use the memory without using the memory, and tables are contiguous. So we will load a single block from relation S that costs us single IO, and we will pass by all blocks of relation R, 800 blocks, because each block can carry 10 tuples, so 8,000 tuples over 10 gives us 800 blocks. And how many blocks are there in relation S? 300, okay, 3,000 over 10 gets us 300, so 300 times 1 plus 800, okay. Let's calculate this. 300 times 1 plus 800. 240,000 IOs. 240,000 IOs. Okay, case 3. They are contiguous and we are allowed to use the memory, okay, to save time. So we have here 800 blocks and we have here 300 blocks. Okay, and we have 100 blocks available to be used, okay, inside the RAM, the memory. So we will load 100 blocks that belongs to S relation, and we will pass by or iterate over all the 800 blocks that belongs to relation R to join them with these 100 blocks of S. Okay, and how many hundreds are there in these 300? Well, 3. So 3 times 900, 100 plus 800, 2,700 IOs. Okay, so that was question 4. Okay, let's solve question number 3. Suppose we have two relations, R of X and Y attributes and S of Y and Z attributes. Assume there is a sorted index on attribute Y for both relations. Let the search keys, for example, Y values, for the tuples of R be in order 1, 3, 4, 4, 5, 6. Also, let the search keys values for S be 2, 2, 4, 4, 6, and 7. Show how you would execute the following join, and also identify the type of your join. Okay, so he gives us two lists of keys for different relations with common column Y. We can use the I think we can use the zigzag join. Okay, so the type of our join algorithm will be zigzag. Okay, zigzag. Okay, so let's visualize this as much as we can. New Discord. Okay, so we have 1, 3, 4, 4, 5, 6. These are the Y values in relation R. Okay, and Y values in relation S. 2, 2, 4, 4, 6, and 7. Let's perform the zigzag join. Let's start here. Okay, let me change the color. Okay, so we stand here right now, 1 and 2. Okay, 1 less than 2, so let's increment this pointer. 3 and 2, 2 less than 3, so let's increment this pointer. Again 2 less than 3, so let's increment the right pointer. Now 3 is less than 4, so let's increment the left pointer. Now we have matching keys. Let's join the corresponding tuples, 4 and 4, 4 and 4, and after that both pointers will point to 5 and 6. Okay, 5 is less than 6, so let's increment the left pointer. Now we have another matching pair of tuples, 6 and 6, and R is exhausted, so we can stop here. Okay, this is the solution. Okay. Okay. Question number 2. Question 2 says, for each of the following operators, tell whether the operator is blocking, by which we mean that the first output cannot be produced until all the inputs, okay, all the inputs has been read. Put it in another way, a blocking operator is one whose only possible iterators have all the important work done by open. Okay, so which one of these will not produce the first line of output until all of the input has been read? Okay, let's take them one by one. Projection operator, okay, works by loading the relation and removing certain columns from each record. So starting from reading the first tuple in a given relation, the projection operator can produce the first line of output. Okay, so new discard. Okay, this is our relation R, and here are the projection operator. The projection operator will iterate over the tuples of relation R one by one, and starting from the first one, the projection operator can produce the output. So the projection operation is not a blocking operator, and the same goes for the distinct operator. The distinct operator will iterate over all tuples of relation R, and if it removes the duplicates. Okay, so starting by reading the first set of tuples, okay, in relation R, it can produce the first line of output. Okay, so it's non-blocking operator, because it doesn't demand reading all of the tuples that belongs to relation R to produce the first line of output. Okay, number 3, the grouping. Okay, the grouping is a blocking operator, because it has to scan the whole table to determine the similar records, okay, to group them. So it demands scanning the whole inputs, so it's a blocking operator. Okay, set union, set intersections, both of them are non-blocking operators. Because if we have relation R and relation S, and S is a smaller one and it already exists in the memory, for each row in R, okay, by iterating over relation R tuple by tuple, for each tuple, okay, starting from the first tuple, this set intersection and set union will produce an output. So it's non-blocking. Okay, it doesn't demand reading all of tuples of S and reading all of tuples of R to produce the first line and output. Okay, and however, the situation is the opposite. Okay, for the set difference. Okay, set difference, if we want to compute R minus S, set difference can be blocking and or non-blocking operator based on which of the relations these two relations R and S is loaded into the memory. Okay, so the first case, if we want to compute R minus S, and S is a smaller relation and it's loaded inside the memory. Okay, so by iterating over relation R, okay, starting from the first tuple, we can reduce the first line of output. Okay, so this way R minus S set difference is non-blocking. However, if we still trying to compute R minus S and the memory, okay, holds M minus 1 blocks that belongs to relation R, to compute R minus S, we need to pass over or load S block by block. So we have to pass over the two relations to print the first line of output. We want to search for each tuple in R into S, and R is loaded inside the memory, so we have to pass over all S to search for the first tuple in R to produce the first line of the output. Okay, so this way the set difference is blocking. Okay, and this applies for the bag difference. The bag intersection and the product and the natural join, all of them are non-blocking. Okay, all of them are non-blocking operators. You can verify it by depicting how each one of them works. Okay, okay, so let's navigate to question number 1, the last question in this practice assignment. Question number 1 asks us to write the logic of the open and get next and close operations for each of the following iterators: the bag union, the set difference, and the projection. Okay, so let's start with the easiest one, the projection operator. This projection operator also eliminates the duplicates. Okay, so the projection operator or iterator works as follows. First, we have to open the relation r.open, and we perform this in the open method. And after we are finished with everything, we have to close relation R in the close method. Okay, then we have to iterate over R tuple by tuple using get next function. So set value tuple to r.getNext, and for each tuple we have to check if it's already exists. Okay, if it's a duplicate, then we will skip it, and if it's unique, we will return the tuple, and the operator or the iterator or database engine has to remove specific columns or attributes from this returning tuple. Okay, so this way we perform the projection tuple by tuple in an efficient way. This is how the projection operator works. Number 1, the bag union. We have already illustrated its pseudocode. Okay, its pseudocode is already stated in the lecture, so it's easy. Okay, the bag union. Okay, we have two relation R and S. We have to open R first and bring all of the stuff inside R into the result set. Then we have to open relation S and brings all of the stuff inside it into the result set. Then we are finished and we have done the bag union. Okay, so at first I have to open relation R and set the current relation variable to R, and after we are finished with everything, we have to close both relations R and S. Let's look at the get next. If the current relation is R, if R is still not exhausted, load or get the next tuple from R. So set T to the next tuple of R, and if R is not exhausted, return this tuple. Else, if R is exhausted, then it's time to open S and set current relation to S. And if the current relation is not R, if it's S, then return S.getNext. Let's exhaust S. Okay, so this is how the bag union operator or iterator work. Okay, the last one is the set difference operator. Okay, let's assume that both relations are sorted, okay, to perform the set difference iterator or operator. Okay, so we have to open the both relations R and S, and of course after we are finished we have to close both of them. Okay, so if we want to compute R minus S, set difference of both relations R and S, so we want to output, okay, or sorry, we want to compute S minus R. We want to compute S minus R. So we will open both relation R and S, and we will get the next tuple from both relations. So X equal S dot get next, and Y equal R dot get next. Then while true, we will repeat doing the following. Okay, if Y equal no more data, if R is exhausted, okay, we will return X, okay, which belongs to relation S. And if X equals no more data, if S is exhausted, then we are finished, so we have to return no more data. And if X equal to Y, then we will return, if they are equal, X and Y are equal, and we want to get all tuples that belongs to S and don't exist in R, so we will skip this and we will increment X by getting the next tuple. Okay, and if X and Y are not equal and the previous conditions are false, then we have two cases. Okay, as we have just said a few moments ago, we assume that both relation R and S are sorted. Okay, so we have two cases. If X is less than Y and R is sorted, so all of the upcoming Y values will be greater than X, then X is impossible to exist in relation R, so we have to return this X. Okay, this belongs to the output set. Else we may find, okay, we may find it later in R, because R is sorted. So let's skip the current Y values and get the next tuple from relation R. So let's visualize it. Okay, here are both relations R and S, and here are the current tuples. Okay, so this is Y and this is X. Okay, if Y equals, and we want to compute S minus R, if Y equals no more data, sorry, this is S and this is R. Okay, if Y equals no more data, R is exhausted, we will return the rest of S. So X equal, sorry, return X. Okay, and if X equals no more data, if S is exhausted and we want to compute S minus R, so we have to stop, so return no more data. Now if X and Y are equal, okay, if X and Y are equal, we will get the next X from relation S, because they are equal and we wanna output the difference. Okay, the last case, if X and Y are not equal to no more data, and they are not equal, so we have two possible cases: if X is less than Y and if X is greater than Y. Okay, let's consider the first one. If X is less than Y, okay, and as we have just said a few moments ago, both relations are sorted. Okay, so it's impossible to find similar value to this X in relation R later down. Okay, so let's output X. Okay, and if X is greater than Y, I may find a similar value to X later here in relation R. So let's skip the current Y value and get the next tuple of relation R. Okay, that's how the set difference operator works, given that we want to compute S minus R, and given the assumption that both relations are sorted. Okay, so this is the end of tutorial 8. Next time we are gonna discuss the merge join, the hash join, and the join with an index methods, and we are gonna solve few problems about how to estimate the number of IOs needed to execute these joins. Thank you, and wish you a good luck. Goodbye.